In this video, we're going to design our first plastic part housing in Fusion 360. Hey everyone, this is Matt with Learn Everything About Design, and in this video, we're going to actually begin designing a plastic housing in Fusion 360. Now, I've given the series a lot of thought, and initially I intended to go in and do a very complex design from the start, but there are a lot of baby steps that need to be taken in order to learn the functionality or the design decisions needed to make plastic parts. So I thought initially we would get started talking about some more beginner-friendly topics. Now, we've already taken a look at why we need a draft, and we took a look at some examples of the reason why we want to be careful with wall thickness on things like internal ribs and bosses, and also things like design decisions required for snap features, snap latches, and how those affect the overall design. So in the description, there's a data set that you can download that includes a housing that's produced by a company called Hammond. Now, these are off the shelf. You can purchase them from DigiKey, from Mauser, directly from Hammond, loads of different places. Now, oftentimes what you can do is you can find plastic housings for your projects and you don't have to go through the trouble of actually making anything. So in this case, what I want to do is I want to talk about this housing and then we're going to create our own housing with some different functionality. Now, I do want to say that this also includes an electronics project that I've been working on, or one that I made. So we're going to include this, and there are some issues in the timeline. And that's simply because I broke the link to all the PCB documents. So there are some warnings or some issues in the timeline, but don't worry about those because all that really matters is that we have the major components, the height of this board, and the connectors that are going to be important to us. So let's talk about this design and some of the things that we need to consider when we're designing our housing. So when I downloaded the Hammond box, which I purchased for this project, it automatically came with a PCB shape. So because the box itself is intended to house a PCB, you can see that it already had a shape that it was intended to use, and it also has things like screw bosses for holding the PCB down. There are some little pads here that the PCB can rest on, so it's supported in the corners. And then there are some bosses that are used to attach it to the other portion of the housing. So there are some interesting design features that happen here that we want to talk about. I'm not going to worry so much about the faces that are inside of here. We're really going to focus on the features that are required. So this housing was interesting in the fact that it uses these bosses. There's a small rib that connects them to the wall, so we don't have a lot of plastic material in the corner causing deformations. But this rib helps with structure, but it also helps with plastic filling these areas. It makes sure that we don't have an area where plastic isn't able to get into or there's an area of extremely high pressure. The small pads also help with stability, but really they're only there to hold the corners of the PCB so that the screw positions can be internal. So this housing follows the basic design principles, and if we hide it and we show the flange lid, you'll notice that this one seems to follow most of the principles, but I noticed that it doesn't actually have any draft on it. And while you can get away with that in some cases, this is probably just a basic representation. You'll notice that there are some pass-through bosses. They come extremely close to the side here, but there is still a gap. And they have some chamfers on the other side, which do help with reducing the plastic thickness in those areas. These openings here are for zip ties to pass through, and then there's a small lip for it to attach to the rest of the box. There's also a section analysis inside of here so we can see inside and see exactly how the box two pieces attach. You can see there's a small lip, there's a little bit of a gap between it, and this helps with alignment when we're putting them together. You'll also note that there is a gap here, and the gap here is really just to help us with pulling the two pieces together. So there is a small gap there, and again, it's sort of a compression thing. As you screw them together, it's going to preload them. So in reality, in the project I was using this on, and projects that I've seen these used on in production, the two pieces were glued together. So this is essentially a glue seam, and having that small gap there actually allows for glue to get in there and it provides a sort of a tighter seal. And then again, the gap between the two pieces helps preload that and get some extra pressure there. In general, that's not necessarily required, but it depends on your application. One thing that you will note that is missing from this housing are any openings for cables or connectors. So the way that I've seen this used in production is most companies will purchase these. They'll use the CAD model for fixturing to hold it, and then they'll create some geometry, maybe a cable pass through or a connector that's panel mounted and epoxied in place, and they'll use that to get cables into and out of the housing. But for our project, what we really want to focus on is the PCB that we have here and the connectors we need access to, which are these connectors on this side, the one on this side, the USB-C for the QT Py. Now, this is a board that comes directly from Adafruit. So it's running a SAMD21 chip. It's great for little microcontroller projects. It has tons of memory. The only thing it's really limited on is the number of output pins, but it has lots of RAM. There's actually an expandable SPI chip that you can solder on the bottom for memory. But again, this board is directly from Adafruit. And one of the great things is a lot of their boards that they develop, you can actually get them in a Fusion 360 schematic or an Eagle schematic. So you can open these up in Fusion 360 in the PCB workspace and bring them directly into your project. So it's great for things like copying the pad locations. If I wanted to solder this directly to my board as opposed to using standoffs, it could do that. So again, it's just nice functionality, kind of outside of what we're talking about here, but just so we understand. So as we're looking at this, I want to use the PCB shape. We're going to assume that we are going to create a housing that's very similar to the Hammond box, but we're going to create it on our own so that we have access to those connectors. So if you were downloading that PCB box from Hammond, then you would have this as a starting point. You could use that for a PCB layout like I did. But again, we're just going to be using this basic shape as our constraint. So we know that we have screw positions in the corners. We need to bolt the board down or use some sort of attachment to locate it. And then we can design from there. So the first thing that I want to do actually in this case is I'm going to save this. And then I'm going to start a new design. And the reason I want to start a new design is because I want to come in and I want to begin creating parameters. The reason I want to create parameters is these will help me define different features along the way, things like wall thickness and draft. So to do this, I'm simply going to go to the user parameter section and hit plus. The first one I'm going to create is called wall thickness. It's going to be in millimeters. I'm going to work in metric for this example, and it'll be 2 millimeters. I want to create another one. I'm going to call this in wall thickness. And this one is going to be my wall thickness parameter. So I'm going to start typing W, select that, and then I'm going to multiply it by 0.6. This is going to give me 1.2 millimeters. Next, I want to create one for draft. So we're going to call this draft, and I need to change the units to degrees. So we don't want to use length, we want to use DEG for degrees, and I'm going to use 2 degrees for my draft. Now, if there are any other parameters that we want to include, now is the time to do it. And any other parameters that we might want to include are things like screw diameter sizes. So these are going to be important, and it's something that we actually have to dig for unless you know exactly what size you're going to be using. So for this, I'm going to go to McMaster-Carr's website. Now, we could do this directly from Fusion 360, and I'll show you that in a second. But in order to download the CAD files, you'll need to create a new account. So you can either log in with your account or you can create a new one. It's free. You don't have to put any credit card information in, but it does allow you to simply add 3D models directly to Fusion 360. We're not going to go through that step because I don't want you to have to create an account just to download screws, but I just at least want to mention it that it is an option. It is extremely handy. So once we're in the main page of McMaster-Carr, I'm going to start by going to screws and bolts. From here, there's a lot to choose from. And when we're talking about plastic housings, whether it's injection molded or 3D printed, we're generally going to be talking about thread forming or thread cutting screws, or potentially talking about threaded inserts. For our example, for most of your 3D printing and for most of your entry-level injection molding, we're going to be specifically focusing on thread forming and thread cutting. So we're going to go into this tapping, wood, and drywall screws area. From here, the easiest thing to do is scroll down on the left-hand side for our filters and there's a for use in. We're going to scroll down until we find plastic and select that. That'll help us with filtering. From here, there's still a lot to choose from, and there are a couple design considerations that we need to be aware of. When we look at these options, there are going to be two main types of screws. And again, we're talking about thread forming or thread cutting. So as we look through here, there's a lot of differences for things like the material, the finish, but we want to exclude ones that are for joining plastic and wood together. So these are not even going to be on our radar. I also tend to avoid pointed plastic screws unless there is a very good reason. And you'll notice that the description here says it's good for centering screws in a starter hole, and this will help reduce the risk of cracking because it's got a fairly wide space thread. However, we typically are going to be dealing with blind holes in plastic, and the pointed screw is just going to take up extra room that we want to avoid having to account for. So a lot of these other screws will typically they'll have like a flat or blunted end. So a couple other things that we need to consider. You'll notice that some of these are for brittle plastic, and when you see these, they'll typically have this sort of a dual helix thread type. When we look at these dual helix thread types, they'll have a very large thread, similar to this pointed one, and then there will be like an intermediate thread. And these are used because thread forming screws is actually taking the plastic material and it's pushing it and deforming it into the shape of a thread. So when you have sort of this dual helix or this dual thread, it gives the plastic more room to expand into, and there's less of a chance of cracking or fracturing the plastic. For us, the route that I would typically go is going to be this thread cutting screw. What we need to do is we need to consider that with thread cutting and thread forming screws, they're generally going to have different hole size requirements. So when you're planning out your project, make sure that you take a long look at your requirements, understand the material that you're going to be using, any requirements there, and then take a good look at all the different screw types available. Some of these other ones here that we're not going to use, for example, these first couple, it's kind of hard to tell from this picture, but they actually have a triangle shaped thread. So three of the sides are flatted or the threads go down to the root, and then it's got the high peaks on the other three sides. So these can also help when we're talking about thread forming because similar to this dual helix, it gives the plastic more room to space out and less chance of it actually fracturing. So for our project, we'll be using thread cutting screws, and you'll notice that these are not metric. Our project is metric, but these are coming in at standard. That's okay because what we can do is we can take a look at these values and we can figure out either a metric equivalent value that we can use, or we can go back to the drawing board and pick another screw. If you're doing this for production, then generally you would want to make sure that you aim for a screw that has the same unit system that you're working in. When we're dealing with things like Phillips head screws, it's not as big of a requirement because we're not really worried about metric versus standard Phillips head sizes. Generally, you have different size Phillips head bits, but they're not going to be metric or standard, like if you were using something such as a hex, or if you had something for an Allen key. Those are going to be very specific to metric or standard. However, they generally allow quite a bit of torque, and I would avoid them on plastic parts, sticking with something like a Phillips head, at least unless you have a specific example. So now that we've narrowed down our screw, we're going to be using the small size, and you'll notice that the diameter is 0.167 inches. If I click on this and I go to product details, and we scroll down, there's no detailed drawing, there's no CAD file with the screw, but again, that's okay. What this really means is we need to focus solely on the data that we have available. So when we look at this, a couple things that we want to make sure we understand. First, we have the diameter and the height. This is the height of the head, 0.062 inches. Now in Fusion 360, if we want to account for this data, what we can do is we can add it in a comment and it'll be stored. So I'm going to add these values. It's going to be diameter 0.167 and height 0.062. So back in Fusion 360, I'm going to open up my comments, and you'll notice that it says that we can't do this until we save our design. So I'm going to save this design. I'm going to call it plastic housing. And once we do that, we should be able to begin adding comments. So again, back in McMaster Car, we have 0.167 inch diameter, 0.062 inch head height. So 167 and 0.062. So 0.167 inch diameter and 0.062 inch. That's going to be head height. So just a few things that we're capturing there. Obviously, if you're working on a dual screen, this is much easier than bouncing back and forth, but I think it's important that we see this data and understand it. You'll next note that they give a drill bit size as a number 49, and the decimal equivalent is 0.073. This is going to be important to us, and we're going to get to that in just a second. The last thing that we want to note is the length here, and we want to capture that as well. So back in Fusion 360, we are going to capture the length, length, and this is going to be 1/4 inch. And again, we can come back and we can make more comments at any point in time, but this is just some basic stuff that we want to capture for right now. The other bit that we do want to capture is the McMaster car part number. So that's this value here. I'm going to just do a Control C to copy it. And back in Fusion, I'm going to paste it here. Gives me information about the price, in stock, and so on. And again, I'm capturing that. So now back in McMaster, the last bit of information that's really critical for us is the diameter. Notice that this diameter and the diameter of the screw itself, 0.086 and 0.073, is different. Now the reason it's different is because we're cutting threads. So this 0.086 is the outside or major diameter of the threads. This 0.073 is going to be slightly bigger than the minor diameter. This gives us enough material to actually go in and cut those threads. So the one that we're really interested in is the decimal equivalent for the drill, because that's the hole size we need in our plastic part. Keeping in mind that our hole will be tapered. So if we have to sort of pick some values and we know the number of threads that are going into our plastic, we want to know that 0.086 is the major diameter and 0.073 is the decimal equivalent for drilling. Because we're going to be using this in an injection molded plastic part, our walls to the screw hole are going to be tapered. So we can't just simply make an 0.073 hole. We need to have some taper. So we need to sort of shoot the difference here. If we bring up a calculator and we do 0.073 and we multiply that by 25.4, that's going to give us our metric equivalent. 0.185 is going to be the closest metric drill bit, dropping off the 4.2. We could also go to 1.9 millimeters, but those are going to be our standard sizes. So the next bit that we want to make sure that we record then is the 0.086, and we're going to convert that to metric, 2.2 millimeters. So we know that our hole can't be bigger than 2.2 millimeters, and we know that it can't be smaller than 1.85. So hole max, 2.2 millimeters, hole min, 1.85 millimeters. So when we go to design, we'll capture that data. We'll make sure that we understand that these are our values that we want to aim for, that 0.185 or 1.85, excuse me, is likely going to be the ideal. And we're going to start from there and taper out, making sure we don't exceed that 2.2. So now that we've got those pieces of information captured, we can go back and go to our change parameters. And we're going to say hole max, and I'm going to set this to 2.2 millimeters, and I'm going to create a hole min. While it isn't strictly required that I capture these as hole min and hole max, there's really no reason that we shouldn't. At least we have this information easily available. So if we want to begin designing the hole from the top and taper it down, we know what our max is. We can subtract a little bit from that in the parameters. So these are the basic parameters that we have and we're going to use to drive our design. I'm going to save this. Then I'm going to open up the data panel, and I'm going to take my electronics housing and simply bring it into this design. What this does is it creates what's called an XREF, or an external reference. I'm going to just say OK for the location. And for this component, I'm going to right-click and ground it. You'll notice that some of the other pieces are hidden. So like the housing is hidden and all the other stuff is hidden based on the current save point in the original design. The reason that I do it this way is because now I have my original design, the PCB component in here, and I still have my modified change parameters, which I could have arguably done in the other design. But this lets me use these external components. So for example, if we wanted to use this PCB in a couple different housings, then we could simply insert it into whichever housing we want. Making sure that we maintain the link here means that any changes made to the design, if this was still linked to the PCB documents, would update in all of our designs. So it's an important step in the process if you are looking at more of a production workflow and you want to maintain the relationship between the PCB and the 3D design, but you don't necessarily want to open the 3D design and have it locked. There is some new functionality coming where you can open up a design just for you. So for example, in this original design, you'll notice that I have read only for me. You also notice in my install that we've got things like release change order, and it happens to come down to the manage extension in my install. But we're not really going to be talking about that. But again, notice at a production level, there are more tools that can make sure that you are not locking the design out for somebody else who's trying to edit. So at this point, we have gone quite a ways into this video. We're over 20 minutes now, and we haven't designed anything. And that's because the setup portion of the design is extremely important. And there's a couple other bits here that I can't really cover that you should do before you design a plastic part. And that is consult manufacturers. Figure out where you want to get your design manufactured. Figure out if this is a low production run or if you're just trying to make a handful of them, and see what your options are. There are companies like Proto Labs that I've used in the past where they will do a 3D print of your design and create a silicone mold for urethane plastics. That's a good low production option. They'll also create aluminum molds for your parts, which means that they don't have cooling channels in them and they're a bit restricted in terms of the number of parts you can get off of the molds. Typically, they like to do 100 to 500 parts before they want to refurbish the mold. And that's because the aluminum molds, as opposed to tool steel, they'll just tend to wear a bit faster. And without having the cooling in them, it's not going to be exactly the same. But the reason I mention this is because the approach that you take for design is going to depend on who's manufacturing it. And it also depends on the volume. If you're cutting parts from tool steel and you're making millions of parts, then you have a bit more flexibility in the design. If you're going with somebody like Proto Labs or another low volume house, then what you end up doing is you make design changes based on their requirements. So I'm not going to go through that process because I don't want to point you in any one direction. I'm not here to advertise for Proto Labs, but I do want to say that the information on their website about their design constraints and the feedback you get when you upload a design to their portal, whether it's for CNC machining or 3D printing or for injection molding, the feedback you get is really great. So as a learning process, if you are designing a part for manufacture, you can upload it to their website. You can check the cost on it based on the number of parts and materials and so on. And it does help. It makes you understand where these potential problems are. But now that we've got that, let's go ahead and think about our design. So I know that we're already over 20 minutes in, and I do want to be mindful of time, but this is basically the first plastic housing that we're going to design. So there's a lot to cover. So we just need to kind of take it slow. So what I want to do is I'm going to start a new component. Whichever component is currently active, in this case the top level, that's going to be the parent. So that parent is going to be important. We don't want to stick it inside of our electronics housing. So what we need to do is we need to call this component whatever we want to name it. In my case, it's going to be plastic housing. Notice that we can activate it, and at this point in time, I'm not going to activate it. I'm going to say OK. I grounded the original electronics component, and I'm actually going to right-click and ground this one. While it isn't strictly necessary, I do like to make sure that the origin of my entire design, you can see it's right there, the origin of my plastic part and the origin that came in for this housing here are all the same. Now, it doesn't have to be the same. Again, that's not a requirement. But when you're working on a design, it's important you know where that is. And the reason that's important is because in this housing, when we go to start sketching, that is going to be the center of our design. So if we want to make use of the center or the origin as a symmetry plane or something like that, then we need to make sure that we move this design so that it's centered about wherever we want. That can be a little bit difficult to do, especially when we have a reference design, but we also have the option to design from the assembly itself. So we can reference things like the bolt holes and the outside shape of the PCB. We can use those as projections in our sketch, and then we can decide how we want to progress from there. So that's the method that I'm going to go. And temporarily, I'm just going to ground this. I'll probably delete that ground later, but this is just going to be the basic setup. I'm going to go back to a home view, and I'm going to hide the origin for right now. So the last thing that I want to do in this video is I want to get started on the layout of the housing. We're not going to be making the plastic part in this video just because I think it's getting too long. But I want to talk about the layout, and then I want to talk about centering what we have about the origin, so that way it's a little bit easier for us to design. With that in mind, what I want to do is activate the plastic housing. I'm going to start a new sketch, and I'm just going to pick the top plane. I'm going to go into my electronics housing. I'm going to hide my PCB and the Cutie Pie, the little microcontroller. I'm going to bring the PCB board that comes in with this housing. I'm going to bring that in. I'm going to select it, and I'm going to use Project Include. So from the Create menu, Project Include and Project, or P on the keyboard. We're going to bring everything in, and we want to make sure that we leave this projection link. That means it'll stay linked to the original. You can see that it brought in the PCB holes, it brought in the circuit board border, we have the center point for all the arcs. So this is great information for us. Now, what I want to do is I want to add to this. So I'm going to hide the PCB so I'm not seeing it. Actually, hide that entire component. I don't need to see it at all. And now I want to find the complete center of this. So it's going to be a little bit tricky because it is not symmetric at all. So what I'm going to do is I'm going to go to this corner here. I'm going to find the middle of this edge. I'm going to go to the middle of this edge. I'm going to find the middle of this edge and go to the middle of this edge. You'll notice that they don't cross at the same place. This one, I need to find the midpoint. There we go. Now that we're at the midpoint on each of these, you'll notice that all three of them cross in one location. This is going to be the exact center of my design, and I want to place that at the origin. So what I'm going to do is I'm going to turn all these into construction lines. You can do that with X on the keyboard, or you can select the option in the sketch palette. Then I want to go to Create, Point, and I'm going to place a point on one of the lines, hit Escape to get off my point tool, and then I'm going to use Coincident and just simply select another line, and that'll place it right at the intersection. Escape to get off of our constraint tools. And now what we've done is we've created a reference that tells us exactly where the center of this is. Now, why is this important? Well, when we finish the sketch, we still have our component, we still have our origin that's located here. What we can do now is we can move the reference of our design so that it's centered about that origin. It gets a little tricky because this is fully constrained, but we can try to use Move Copy. We can try to use Sketch Objects and see if we can select them all. You'll notice only the ones that we created are able to be moved. The rest of it is not able to be moved. So another way that we can get around this is by creating a solid body as a reference, and then that solid body can be moved a little bit easier. So what I want to do is I want to extrude this out. I need to know how thick the PCB needs to be, but for right now, I'm going to say 1 millimeter, and I'm going to say OK. So now we have this solid body. I can bring the sketch back, and now I'm going to say Move. I'm going to set it to Bodies, but I want to reset my pivot point. I'm going to put my pivot point right here at the middle. I'm going to say OK, and then I'm going to say Move Point to Point. This will keep the orientation of the body the same, and it'll simply move from our selected origin point to our target point. So when I move that, you'll notice the whole solid body moves. It stays in the same orientation. It hasn't rotated at all. It just simply shifted from that point to this point. We're going to say OK. I'm going to hide my sketch, and then I want to bring back my housing. And the reason I want to do this is because my PCB that's part of that housing, you can see exactly where it's located. So if we bring back and activate the top level, this is where we need our PCB to be. This is where our reference is going to be for our board and the Cutie Pie to make sure that all of those different pieces are in the right place. So now what I need to do is I need to move my entire component to that location. This means that this pin that I created, I don't need it anymore. Now while we could unground it, I'm just going to right click and delete. And because nothing really moved and no positions were captured, it doesn't matter. It doesn't affect anything else in the timeline. But now we want to move this board down to here. So here's the interesting bit of this. There are a couple different ways we can do it. We can use move again, but we need to make sure we're moving the entire component. And we can't go origin to origin because they're already in the same location. So what we need to do is we need to pick some reference geometry. And since we projected this entire board, we can now move this thing wherever we need to. So we can use move copy or we can use align. Either one will be fine. I'm going to use align in this case since we've already looked at move copy. Change it to bodies. We're going to select the body, but notice that when we do this, we really need to select a reference point. And oftentimes when you move around, it can be hard to actually select the right point. On a PC, we're going to hold down Control on the keyboard, and that'll let us lock our focus. Then we want to select where we're going to. So again, we can hold down Control, and it pushes them right to the correct spot. We're going to say OK. And now if we look at the origin for our plastic housing, and we look at the origin for this, you can see that it's in the same location. But what does that mean? We really wanted to move this entire component. But the component didn't move, only this body moved. So let's Control Z, let's undo and put this back. And let's make sure that we are moving the entire component. So that's going to be the big difference here, is because we want to make use of symmetry. We want the center of anything we design to be at the origin. It's going to help us if we're trying to create a unique or organic shape by using those origin planes. While it isn't, again, strictly required, I find it's the best practice to make sure that our designs are about the origin. So once again, let's go to Align. Make sure that we are set to Components, and that's going to be the big thing. And instead of selecting the body on the screen, select the entire component. And then the To position, we're going to select a position, and notice that that doesn't work. Why doesn't this work? And that's really because we selected the component. We didn't give it any reference location. So let's cancel the From selection, and in this case, hold down Control and select that same point. Now you can see it worked, and now we have a Capture Position option. This is going to be important. We're going to say OK, and now let's double check our origin. The origin is at the center of our board, and if we bring back the origin for our components, you can see that it's up there. So now we got it to work just right, and the key to that was, again, making sure we're moving the component based on a selected reference. This is still not locked in place, and neither is this one. They're free to move about. So we do want to make sure that we ground them as needed. Now, ground is simply just a way to tell Fusion 360 that the origin of this component is not translating or rotating at all. And again, while it isn't strictly necessary, if you find yourself accidentally moving components around, it is important. And on that same note, we grounded the top level of our electronics housing. But if I bring back any of the components, note that I can freely move them around. And that's because the top level has its own origin, and each other component has its own origin as well. And you'll notice that they're different. In some cases, it'll be at this corner, and that's because the PCB is designed in that positive quadrant. In other cases, it's wherever the housing was located. So if you want to ground everything, you need to make sure that you simply make a rigid group of everything, or that you ground them. And the rigid group is probably the easiest option because we can select the housing, go to Assemble, and we can create a rigid group. Notice that the rigid group is going to include child components. So we're going to say yes, and that'll mean everything underneath this is going to be locked in place. Now we can't move that. We can't move anything else that's associated with it because they're all considered rigid. So this is a quick way for us to lock everything in place without having to ground everything. So that was a lot of work for not a lot of results at this point. But it was important that we understand how to set up our designs to make sure that we're making use of the origin, we're making use of our coordinate system, and we want to design centered about the origin whenever possible. If you're making a design that goes on a PCB that's rectangular or circular or symmetric in any way, making use of the origin at the center of that design is going to save you a lot of time. So at this point, I think that's a great place for us to save. I know that we haven't really made much progress, but keep in mind that we're doing all this setup now so that the design bit will be easier. Just a quick reminder, we created a new design and we created some user parameters. We have wall thickness, the inner wall thickness, draft, hole max and hole min values for our screws. And we also added some comments about the screws, the hole min and hole max, the part number, the length, the head diameter, and the head height. That's going to be important if we're doing any counterbores to sort of keep the head size out of the outside of our housing. And we also took a bit of time to set up a new component and make sure that that new component is centered about the origin with our PCB shape. While we took a couple steps that weren't strictly necessary, they do help us downstream. The creation of the user parameters, the locating of our component at the origin, those are all bits that are going to be important. If any of the components from the electronics design had been centered about their own origin, this would have been a lot easier, but I find that that's usually not the case. You bring a design in, and the origins will be all over the place, and you need to take a little bit of time to create a reference sketch, maybe even a reference body, to help locate those as needed. So that setup work is going to be important, and it will save us some time downstream. One of the things to note is going forward, I'm not going to continually share the design because once we have an external link or an XREF, it becomes a bit trickier for us to share and I'll have to break the link. But for right now, I want to maintain that link and I don't want to export any F3Z files because those references will just get trickier for us to deal with. So I think that you should follow along. I will be providing a data set at the end where I break the link. But if you want to learn to design, I think it's important that you take these steps on your own. I will continue to go through the process slowly because I do think that there are several important steps along the way that we need to understand. That way you can progress with your own skill. In the meantime, between videos, I always find it helpful to take apart plastic designs around your house, especially if you're just doing things like changing the batteries in a device. Remove the battery door and take a close look at how it was produced. You'll find that they use some very interesting tricks for things like slides and snap latches. That way we can create openings from one side of a part, and we don't have to get extremely complicated molds to make that happen. So that's a great learning opportunity, and I do it all the time, especially when stuff breaks. Take it apart, see how it's put together, and you'll find some very creative solutions to things like holding PCBs down without hardware. When you're talking about creating these for hobby reasons, it doesn't really work. It doesn't matter if you save a few milliseconds here or there. But if you're assembling millions of units and you can simply push a PCB down and snap it into a plastic housing, as opposed to having somebody attach two screws, that saves loads of time and in the end, a lot of money. So at this point, if you're following along, make sure that you do save your design. And as always, thanks for watching and we'll see you in the next one.